My name is Alex Carlson, and I'm a recent graduate from the Civil and Environmental Engineering College at Old Dominion University. And last semester, I led a team of ODU civil engineering students in adapting a historic waterfront neighborhood for sea level rise in Norfolk, Virginia. So, looking at the overall issues in the neighborhood, from talking to residents and looking at the information that was available from the city and topography, flood maps, etc., we identified a few issues from our analysis. The first one was a very steep shoreline, an eroded shoreline, which is close to existing streets and homes. And this doesn't give a very good buffer area or a retreat area when the tide starts to rise, and this again will get worse with sea level rise. The other issue that we found was the existing stormwater infrastructure and storm pipes were found to be fairly small, and a lot of them can be inundated during heavy rainfall events. And as the tide rises in a storm surge event, the pipes actually will become inundated with the water from the river, the storm surge from the river, before the rainfall actually is entering the pipes, making the situation even worse. Lastly, we looked at the entrance into and out of the neighborhood along Kimball Terrace, which has an existing culvert underneath the road. And we found that the road dips down in that culvert crossing, and this could lead to flooding issues on top of the road. And along with the culvert being fairly old, might not be able to pass the stormwater through the culvert during a large rainfall event. So to analyze the existing stormwater network, we received GIS data from the city of Norfolk, and we were able to build a EPA SWIM model. SWIM model is a free open source stormwater modeling software put out by the EPA, and it allowed us to model the network of the existing pipes. And using the city's standard 10-year rainfall event, which is a once in 10-year storm event, we could set a benchmark for the performance of the system. We could target areas that received a lot of volume of flooding in the model, and then we could adapt our solutions around those areas that our model was showing us. And it was interesting because we were also able to get maps and talk with the residents to see where their flooding was and kind of overlay those two and see where the flooding of the model also matched up with some of maybe the citizens' reports of the flooding. So by setting that benchmark and understanding where the problem areas were, then we could tailor our low impact development designs around the areas that we saw issues and put them into the model and actually see what the reduction of flooding from these rainfall events would be. We used the 2009 nor'easter, nor'easter, as it was a devastating one to the region, and based on citizens' accounts was devastating in that area of Norfolk and the Chesterfield Heights neighborhood. And after implementing the low impact development solutions, we saw reductions of up to 90% for the volume of floodwater at some of these drainage inlets, just by directing it to bioretention cells, pervious pavement, and other stormwater management practices like that. So looking at the project from a stormwater perspective, and to address some of the issues that we were finding from our preliminary modeling, we wanted to really use the landscape to absorb more of the stormwater, and at the same time this would cut down on flooding at the inlets, but also treat the stormwater and remove pollutants that are harmful to the river and the Chesapeake Bay. So really we wanted to optimize and get as much benefit from these type of practices as we could. And that's why we chose low impact development stormwater management practices, which gives us not only that pollutant removal, but also gives a designated area for the water to go and to infiltrate into the ground. After looking at soil surveys of the area, we identified the area as having sandy soil, which would be good potentially for infiltrating that water back into the groundwater during heavy rainfall events. So I think it was critical for our group to be able to go to the neighborhood, walk around, take photographs, even go out during rainfall events and see how the neighborhood responded to a rainfall event, see what the topography was, see the feel of the neighborhood. This is a historic neighborhood, so we wanted to keep that in mind with our design. Along Marlboro Drive, there's a brick road that was existing, and that kind of influenced the way that we took some parts of the project, going with the pervious pavers, which we could kind of seamlessly tie into that existing historic road. I think you don't get those types of insights when you're just looking at a map or looking at a computer screen. Really being able to go out to the site, I think, was crucial for our solution. Talking to members of the community, getting a sense for the pride that they had in their community and getting a sense for some of the issues that they were dealing with on a day-to-day basis from these type of rainfall and storm surge events, getting a good sense of what areas might be a little more troublesome for them. Maybe you can't, drive your car through that area or that intersection, or, oh, that road, might flood during a storm surge. That kind of real world kind of data is valuable in the engineering sense too. It's also great to put faces to these, the homes and the streets. So now that I've graduated with my bachelor's in civil engineering from ODU, I'm going to be working at Kinley Horn in Virginia Beach, doing land development and dealing with a lot of these issues regarding stormwater all throughout this region. And it interests me because it's a challenge. Given this area's low elevations and inundation from storm surges and rainfall events, it's not very easy. And every single site and every single neighborhood has different challenges, just as we found in this project in Chesterfield Heights.